An ASCII table connects three important things: a character, its decimal code, and its binary code. For example, the character A has the decimal code 65, and 65 in binary is 01000001. So we can say A equals 65, and 65 equals 01000001 in binary. In the same way, B is 66, and C is 67. Using an ASCII table, we can easily move between characters, decimal codes, and binary codes. This is how computers represent and store text using numbers. Now let's find the ASCII code for the character G. First, look for G in the ASCII table. We can see that uppercase G has the decimal code 71. Next, we look at its binary representation. Decimal 71 is written as 01000111 in binary. So, G equals 71 in decimal, and 71 equals 01000111 in binary. Remember, uppercase letters have ASCII decimal codes from 65 to 90. Using the ASCII table, we can easily move between a character, decimal code, and binary code. Now let's convert the character A into binary. From the ASCII table, uppercase A has the decimal code 65. Next, we convert 65 into binary using the 8-bit place values. We can make 65 using 64 plus 1. So we place a 1 under 64 and a 1 under 1. All the other positions contain 0. This gives us 01000001. So, decimal 65 equals 01000001 in binary. Therefore, the ASCII binary code for uppercase A is 01001. Now let's convert lowercase a into binary. From the ASCII table, lowercase a has the decimal code 97. First, break 97 into powers of 2. 97 equals 64 plus 32 plus 1. Now, using the 8-bit place values, we put 1 under 64, 1 under 32, and 1 under 1. All the other positions are 0. Reading from left to right gives us 01100001. So, 97 in decimal equals 0110001 in binary. Therefore, lowercase a is represented as 0110001. Now, let's convert the ASCII decimal code 84 into binary. First, break 84 into powers of 2. 84 equals 64 plus 16 plus 4. Using the 8-bit place values, we put 1 under 64, 1 under 16, and 1 under 4. All the other positions are 0. Reading the bits from left to right gives us 0101, 0100. So, 84 in decimal equals 01010100 in binary. From the ASCII table, decimal 84 represents the character T. Therefore, uppercase T is represented as 01010100 in binary. Now, let's convert a binary ASCII code back into a character. We are given 01000011. First, look at the positions containing a 1. We have 64, 2, and 1. Now add these values together. 64 plus 2 plus 1 equals 67. So, 01000011 in binary equals 67 in decimal. Next, look up decimal 67 in the ASCII table. We can see that 67 represents uppercase C. Therefore, 01000011 equals 67, which represents the character C. This is how we convert from binary to decimal, and finally, to an ASCII character. Now let's decode these binary values into text. We have 3 8-bit binary values. Remember, each binary value represents one character. First, 01000011 converts to decimal 67. From the ASCII table, 67 is C. Next, 01000001 converts to decimal 65, and 65 is A. Finally, 01010100 converts to decimal 84, and 84 is T. Now, put the 3 characters together, CAT. So these binary values represent the word cat. To decode ASCII text, remember the process: binary to decimal to character. Now, let's convert the word DOG into binary. First, find the ASCII decimal code for each letter. D is 68, O is 79, and G is 71. Next, convert each decimal code into 8-bit binary. 68 becomes 01, 0001, 00. 79 becomes 01, 001, 111. And 71 becomes 01, 000, 11. Now, combine the three binary codes, so the word DOG becomes 01, 0001, 00, 01, 001, 11, 01, 000, 11. Remember, each character is represented by its own 8-bit ASCII code. So the process is text to decimal ASCII code to binary